Okay, so last time we started talking about bonding. So we talked about really, the two major sort of classes of bonding. We have our we have our ionic bonding, and our ionic bonding is between a metal and a non-metal. And when we have an ionic bond between a metal and a non-metal, as we talked about with basically the periodic trends and such, what ends up happening is when that metal and non-metal get together, the metal pretty much is willing to sort of give away its electrons, and the non-metal is willing to pick up the electrons. And that results in the metal losing electrons, becoming positively charged and an anion, while the non-metal, on the other hand, will pick up those electrons and then obviously become negatively charged or an anion. The important thing to remember with ionic bonding, as we talked about, is there is absolutely, positively, really no sharing of electrons happening there. What is holding that sort of unit together is that positive negative attraction between the two ions, and that's basically the unit that holds it together. Now, the other type of bonding occurs when we get a couple of nonmetals together. So when we get two nonmetals together, we get what's referred to as covalent bonding. Covalent bonding is different than ionic bonding in the sense that because they are basically both nonmetals, they are both basically hanging out over here in the same part of the periodic table. They share very similar trends in terms of those electronegativity, things like ionization energy, electronegativity, electron affinity, size. And all of those sort of trends taken together basically means that when we put two nonmetals together, we're not going to get somebody that basically will take an electron and accept an electron. We're not going to get that transfer of electron. And that's because they both essentially in that bond want to actually take the electron. So what we end up getting is some cooperation, I guess you could think about it that way. We get basically two guys that will share electrons. And when those two atoms share electrons, as we talked about as well, sometimes that sharing is considered sort of equal sharing, which means that basically the electrons sort of stay equal sort of presence on both sides or near both of the atoms, nucleuses in that case. And sometimes we get some unequal sharing where one of the atoms in the bond basically is kind of tugging the electrons closer to itself than the other. Now, when we get that equal sharing, that is what is sometimes referred to as a nonpolar covalent bond or just a nonpolar bond. When we get that unequal sharing that occurs between two nonmetals, that is what is referred to as a polar bond or a polar covalent bond. What determines sort of how those electrons are going to be shared, between the two atoms, it really is what we sort of finished up on, I think, last time, which was electronegativity. Electronegativity is the ability basically of an atom to bring electrons towards itself. And as we see in this slide here, and as we've talked about a number of times, electronegativity increases as you go up and to the right on the periodic table, with, as we can see there in the top right corner, fluorine being the most electronegative element that we have, with a value of 4. And electronegativity decreases as you go left and down on the periodic table. And that is really, sort of the basis for when we talk about bond polarity. And bond polarity, a lot of times we use just the difference in electronegativity values, like we see on this table, to help us decide what type of bond would happen. Now, when we take the difference in electronegativity values, we basically are simply just subtracting the two values for the elements that are involved in that bond. And if we get a difference that is from 0 to, say, 0.4, that is considered a nonpolar bond. If we actually get a difference of exactly 0, it's still a nonpolar bond, but some people will also refer to that as a pure covalent bond, like perfect sharing of those electrons. If we get electronegativity difference that's like above 0.4, so like 0.5 and above, and 0.5 to just below 2, that is considered a polar bond. So if that difference in those two electronegativity values ends up somewhere in that range, is considered a polar bond. And lastly, typically speaking, not 100% always the case, but in most cases, if we get sort of a difference that is greater than 2 in terms of electronegativity, we consider that to be an ionic bond. Where that difference usually arises from is basically when we take a metal and a non-metal together. So if you look on these electronegativity values here on this table, you can see on the left-hand side, they have very small values. On the right-hand side, they're more larger values. So when we kind of put a metal and non-metal together that come from opposite sides of the periodic table, we are going to get that electronegativity value difference of, 2 or more, usually in a lot of cases. And that really will indicate an ionic bond. As I mentioned before, a couple of things about that. Obviously, if you know it's a metal and non-metal, you absolutely don't even need this table. It's going to be an ionic bond, I would say, in 99.999% of the time. Other things and other situations where you might not need the table is if you're comparing two elements that are in the same period on the periodic table, like I think we talked about at the very end, we looked at carbon and oxygen. Again, they're in the same period, which means there's going to be a polar bond because oxygen is further to the right and they're in the same period. So oxygen should be more electronegative than carbon, and that would probably result in a polar bond. Also, if they're in the same group going up and down on the periodic table, you really don't necessarily need the values to make that determination. You can pretty much do a pretty safe determination by looking at the positioning of those two. So there we circled, I think, nitrogen and phosphorus, again, both in the same group. We would anticipate that nitrogen should be more electronegative because it's higher up, and phosphorus should be less electronegative, which we actually do see with the values when you look at the table. And that also should result in a polar bond. So there are certain situations where you could really, without even the actual numbers, kind of make that determination pretty safely in terms of will it be a polar bond or not be a polar bond, just by the general trend in electronegativity. Another thing that we did talk about was the idea that there is a diagonal relationship on the periodic table in terms of some elements and their electronegativity values. So as we can see here, just looking at this one, carbon and sulfur, although they are two different elements, they both have the exact same electronegativity value of 2.5, which means that they would actually share those electrons equally. We also see a similar relationship if you look at nitrogen and chlorine. And that was that diagonal relationship that we talked about, that although, for example, carbon is further up on the periodic table, sulfur is basically further to the right, and they're almost sort of, as we talked about, diagonal of each other. So the differences essentially cancel each other out, and they end up with the same electronegativity value. The last thing that we sort of talked about in terms of bonding was the idea that pretty much the whole goal of bonding is for everybody to reach the same electron configuration as the noble gases. And we saw that already looking in terms of using Lewis dot symbols to represent ionic bonding. Lewis dot symbols are the symbol with one dot for each valence electron in that particular atom. And remember that when we do draw sort of those Lewis dot symbols to indicate ionic bonding, what we are seeing is actual transfers of electrons and accepting of electrons. And that means when we draw those structures, there should be charges associated with it because they really are ions. And what we see is that metal pretty much will lose electrons and go backwards to the noble gas that comes right before it. The non-metal will pretty much go forward when it accepts those electrons, and they both are able to achieve noble gas configuration by gaining and losing electrons. That's the exact case, for example, with our sodium chloride that we're looking at. The sodium there will lose one electron. That will back it up to the same electron configuration as neon. and the chlorine will gain 1 electron, which will allow it to go forward on the periodic table to basically argon's configuration. Now, when we're doing covalent bonding, we're still really trying to achieve that and getting everybody to that group 8 type situation. And that's the idea behind the Octet Rule that we talked about. The Octet Rule, again, is the ability of everybody to keep making bonds until they have 8 valence electrons around them. Those 8 valence electrons essentially indicate that they have hit that noble gas configuration. The one very important exception to that is hydrogen. So I think, as we talked about last time, hydrogen only needs to get to helium. That is the noble gas that comes after it on the periodic table. And that means that hydrogen in a bonding situation should definitely only have 2 electrons. Whew, that was a mouthful. Any questions on any of that stuff we talked about last time there? All right, so we will then pick up here and continue talking. So as we've seen and as we sort of talked about, again, atoms that have pretty wide difference there in electronegativity values typically will result in those electrons being transferred, and that's going to really result in our ionic bond happening. And again, that happens with our metal and non-metal, which are pretty much on opposite sides of the periodic table. Obviously, guys with very similar electronegativity values are going to lend to some type of covalent bonding, again, either a polar bond or a non-polar bond, but there's going to be some type of sharing of those electrons, as we talked about. Essentially, that's sort of the best that they can agree upon because they're both non-metals. And that pretty much summarizes what we've been talking about, that ionic bonds, as soon as you see a metal and non-metal, you should automatically know it's an ionic bond. And when you see 2 non-metals, you should know that it is some type of sharing of electrons that are happening in that particular case. And that's sort of the rule we talked about there. Another sort of way that sometimes, come back here, that sometimes bonding is described is through this. It is what is sometimes referred to as percent ionic character. And percent ionic character basically means that if you have an ionic bond, you obviously have 100% ionic character, which essentially means that there are no sharing of electrons. We basically have a transfer of electrons that occurs. If you have a pure covalent bond, it has basically no ionic character. And what that basically means is, instead of those electrons being transferred like we would see in an ionic bond, again, they're going to be shared when we look at it. So now that we talked about sort of the background here for bonding and covalent bonding, let us actually talk about how we draw these Lewis structures for covalent bonding. Now, there's a couple of things that are really important when we do this. And the first thing is, if you follow sort of these rules we're going to talk about, you will probably end up with a pretty good Lewis structure picture. If you decide to draw your Lewis structures for covalent guys, how some people tend to do it, which is what I call kind of piecework. Like, you take each of the elements and atoms individually, each of the Lewis dot symbols, and then you try to figure out where this electron goes, and this electron goes. Usually you'll end up with a pretty crappy picture there. You'll end up with something that has too many electrons, not enough electrons, and stuff like that. So if you really do follow these sort of rules we're going to talk about here, it will probably, in most cases, I won't say 100% of the time, but in most cases, it will probably lead you to a pretty good Lewis structure in terms of the one that you draw. A couple important rules, obviously, when we're talking about drawing Lewis structures for covalent bonds, is those 2 that we just talked about. Again, sometimes referred to as the duet rule there for hydrogen, is only 2 electrons. Everybody else is heading for that octet rule, which needs 8 electrons. So one of the first important things to think about is, when you're drawing a Lewis structure, is how the atoms should be arranged to each other. In most cases, and in a lot of things that we do draw, there's usually like a center atom and everybody else is attached to it. There could be situations where there is multiple center atoms, but a lot of times, kind of the simplest arrangement is like one guy in the middle, everybody else sort of attached to it. So, how do you know what maybe should end up in the middle of a structure? Well, there's a couple of rules that will help you sort of decide that. First one is, in general, we like to put the least electronegative atom in the center. So usually when you're drawing these pictures, you want to end up with the least electronegative atom in the center. We never find hydrogen in the center, and we never usually find fluorine in the center because obviously fluorine is the most electronegative. We again don't find hydrogen in the center because it should look like this, which means if you put hydrogen in the center, it's bound to have way too many sort of electrons bound to it. Once you got sort of a logical arrangement for how, this sort of molecule should be put together, the next thing, which really for the most part is the most important thing, is to figure out the total number of valence electrons. So you want to figure out the total number of valence electrons that are available in your drawing. That obviously goes to the periodic table, the group number equaling the valence electrons. We also want to make sure, though, that if we do have a charge, so perhaps we're drawing a polyatomic ion, so that is something that's actually covalently bonded but has a charge still. And if something does have a charge, we need to adjust our electron count for that. So if something has, again, a negative charge, that means that it has gained electrons. So we need to add that to our total. If something has a positive charge, that means it lost electrons, which means we need to subtract that from our total. And that's really important. That number is really important because when it is all said and done, you need to have exactly that number in your picture. You cannot have one electron more, you cannot have one electron less. You need to hit exactly that number when you do your drawing. Once you have the logical arrangement, once you know how many total electrons your picture should have, the next thing you want to do is basically make a single covalent bond from the center atom to each of the outside atoms. So you basically want to draw one single line from the center guide to all the outside atoms. Each line, if you remember, will count for 2 electrons. So you want to figure out how many electrons you have left after you do that. Then all the leftover electrons should go on the outside atoms in pairs until each of the outside atoms have basically hit the octet rule, or it has hydrogen, which shouldn't have any dots on the outside. If you fill up all the outside atoms with those dots and you still have more electrons to put on the atom, then you should go to the center atom and put them on as dots. Once you have sort of successfully distributed all of your electrons in the form of dots around everybody, what you want to do is make sure that you count up everything and make sure that everybody in that picture has 8 valence electrons around it, except for obviously hydrogen that should only have 2. And it's at that point that if you have used up all your electrons and somebody does not meet the octet rule, you should then try to fix it by making a double bond. And after you try to do all the double bonds that are possible, and if it happens to still not fix it, then you should make a triple bond. So in most cases, it's not the greatest idea, and people always want to kind of do it. People always want to kind of double bond and triple bond like right out of the box, and it's usually not the best idea. So we want to think about saving double bonds and triple bonds for situations where we are not able to meet the octet rule. That's sort of where we want to use it. Any questions on that there? Okay, let us look at one here together and see. So let's go through these steps together so you can kind of see it in action here. So let's say we wanted to draw the Lewis structure for nitrogen trifluoride, that is NF3. So one of the first things that you would want to do is really count up the total number of valence electrons. So if we went to the periodic table, we would see that nitrogen is group 5, which means it has 5 valence electrons. There are 3 fluorines. Each fluorine is group 7, which means it has 7 valence electrons. There's a lot of math there, but I can go with 26 valence electrons on that deal. Now, in this particular case, we could think about sort of a logical arrangement, and logical arrangement here would be nitrogen in the middle, as it obviously is the least electronegative. Fluorine being the most electronegative, again, would not be in the middle. At this point, we have our logical arrangement. We got our total number of electrons. The first thing you want to do is just simply make one single bond to everybody. There we go. So if we count up how many electrons I just used, each line is 2 electrons. I basically just used 6 electrons there in my picture. That does mean that I have 20 more to go. So those 20 electrons will go on the outside in pairs. So that would be 2, that would be 4, that would be 6. That fills that guy up. Continue on to the next one. 8, 10, 12. That fills that guy up. 14, 16, and 18. That fills that guy up. I've now just put 18 electrons on there. That means I have 2 more to go. I have completely filled up everybody on the outside. So at that point, since I still have 2 electrons to go, those 2 electrons will end up right there as pairs on the central atom. At this point, I have now put on there a grand total of 26 valence electrons, which is what I should have. I want to make sure that everybody there basically meets the octet rule. So this guy's got 2, 4, 6, 8 electrons. Guy over here is the exact same, 2, 4, 6, 8 electrons. Guy here is 2, 4, 6, 8 electrons. And our nitrogen, 2, 4, again, 6 through sharing, and 8 electrons. So everybody here has just met the octet rule, and that would be the proper structure here for our NF3. Any questions on that there? So if you follow those steps, you should really end up with pretty good structure when it's all said and done. You can see I didn't do it by piecework. And again, by piecework, what I mean is sometimes people, you know, they'll go, okay, well, nitrogen is 5, fluorine is 7, this fluorine is 7, you know, this fluorine is 7, you know, and they try to figure out, well, this goes here, this goes there. And usually what you end up with is sort of a very bad picture, something that, you know, again, has too many electrons, too less electrons. Any questions on that one there? Okay. So why don't you try this one, see what you come up with. Why don't you do CO3 2 minus. So why don't you draw carbonate and see what you come up with, how we're doing here. So when we look at this, first thing we want to do is really kind of add up everything that's going on in terms of the valence electrons. So carbon is group number 4 on the periodic table, which means it has 4 valence electrons. There are 3 oxygens. Each oxygen is group number 6, obviously, so that is 6. And now this is a polyatomic ion. It does have a -2 charge. And the -2 charge means that it actually did gain 2 electrons. So we do need to adjust our count by adding 2 again for the negative charge here. And that is going to get us 24 valence electrons in that case. Any questions on that there? Okay, so next thing is logical arrangement. Well, obviously here we have 3 oxygens and 1 carbon. It would make sense that carbon should probably be in the center. All the oxygens are bound to it. Again, if you remember what we were talking about earlier as well, just in case you're not sold on me telling you that, you could look at the periodic table here. And we got carbon, we got nitrogen, we got oxygen. So just by thinking about electronegativity and the trend, since carbon and oxygen are in the same period, we do see oxygen further to the right, which means we would expect oxygen to be more electronegative, thus carbon being less electronegative. So it would make sense to put the carbon in the middle and the 3 oxygens on the outside. Now you may be asking, does it matter, like in this particular example or the previous example that we did, that, for example, here I put the oxygen up on top? Could I put the oxygen on the bottom instead? You can. And just like in the other example, I put the fluorine on the bottom and nothing on top. You know, could you attach the fluorine to the top? And you absolutely could. It really doesn't make a difference in that sense. So what we want to do is the same approach as we've been talking about. We want to pretty much lay up one single bond to everybody. So we're going to do a single bond that way, a single bond that way, and a single bond that way. That again is going to take us 6 electrons off. That's going to leave us more left over. Is that 18, I think? So 18 electrons to go. Those again are going to now go on the outside in pairs till we fill up each of the outside guys. So that is 2, that is 4, that is 6, that now is 8, that is 10, that is 12, that is 14, that is 16, and that is 18 in this particular case. At this particular point, if we take a peek at what we got going on here, we have used up all 24 electrons here. So all 24 electrons have been placed. So what we want to see is, are we good in terms of 8 electrons around everybody? And in this particular case, exactly, carbon is not good. It does not meet the octet rule. If we look at the oxygens, we got 2, 4, 6, 8. All the oxygens are exactly the same, which means they all have 8, but carbon, as you correctly pointed out there, has only 2, 4, and 6 electrons. So here carbon did not meet the octet rule, and that means that A, this is not the correct structure. We can't really leave it like this because it really doesn't meet that octet rule. So what do we do to fix it? Well, we need to get carbon to pretty much 8 electrons. So we can obviously just do that move right there, which is probably not a good move either. In this case, that obviously now gives us 26 electrons, which is not right. So we cannot do that. We can't add it. So as it also was said there in the chat box, we do want to do a double bond to fix that. In this particular case, it doesn't really matter where we make the double bond. We could actually do it at any of the oxygens. They are all equivalent with each other. The deal, though, is we cannot just lay up a double bond like so. And the reason we cannot lay up a double bond just like that is because we now have, again, too many electrons. So when we make a double bond or even a triple bond, what we are actually doing is taking a pair of electrons and we're going to basically bring them in to make that double bond. And when we do that, we will end up with a structure, for example, for carbonate that looks something like this. And what we should do also is Put a little bracket around it and a -2 charge since it does have a charge. But if we go around and start counting everybody, oxygen on the left has 2, 4, 6, 8 electrons. Oxygen on the right, 2, 4, 6, 8 electrons. Double bonded oxygen, 2, 4, 6, 8 electrons. And now the carbon has 2, 4, 6, 8 electrons around it. And we still have only 24 electrons, which means everybody now met the octet rule, 24 electrons. And this would be a proper structure for carbonate. Questions on that there? Now, we absolutely could have double bonded here. We could have double bonded here. And if you did that, it would create a different structure, sort of. We will end up with, if I double bonded to the right-hand side there, we would end up with the double bond over here. And if I double bonded to the left-hand side, we would end up with this structure over here. And these three structures are related to each other by this nice arrow here. And these guys are what are known as resonance structures. And resonance structures really do develop basically like we just see here. In this particular case, because all three of these oxygens are equivalent to each other, we could have double bonded at any one of these guys, and that gives us three equal resonance structures. The true structure is probably somewhere between all three of them, and that's because those double bond electrons are what are referred to as being delocalized, which means they're just kind of flying around, which means at any given time, they may be over here on the left-hand side, maybe at the top oxygen, maybe on the right oxygen. And again, you'll sometimes see that demonstrated in books and stuff where they'll kind of show something like carbonate and have like a dotted sort of line to represent. Again, those electrons are sort of moving around. This is not a proper Lewis structure, just so you know, just to demonstrate though that the electrons are moving around. So we oftentimes will draw resonance structures when we do come across a structure where, you know, you do have more than one sort of opportunity, I guess, to put it, to make a double bond in a different location, and even maybe it's triple bond in some cases, and we could come up with some different structures. Again, if you were not asked to draw all the resonance structures, you could draw any one of these three guys in the middle, and it would be perfectly acceptable. If you were asked to draw all the resonance structures, you would technically need to draw all these guys here. And again, resonance structures are usually indicated by these arrows heading in both directions in between the two. Any questions on that one there? So again, here you can see we didn't really double bond right out of the box. We sort of saved it and to sort of fix a problem. All right, why don't we try a few more? Excuse me. So why don't you take a few minutes here? Why don't you draw SO2? Why don't you draw nitric acid? Why don't you draw the Lewis structure for ammonium? Why don't you draw it for H2S? Why don't you do nitrogen? And why don't you draw it for ClO3 minus? So take a few minutes here, draw the proper Lewis structure for each of these, and we will go over it. I'll give you a hint on nitric acid in terms of the arrangement. One of the hydrogens, or the hydrogen is attached to one of the oxygens, and nitrogen's in the middle. So something like this, just in case you're not sure sort of how nitric acid would look. All right, why don't you take a few minutes here and see what you come up with, and then we'll compare drawings and see how we did, at least on some of these. So we'll start on the left there. We'll start with our SO2 and see what we come up with. So on our SO2 here, just gonna draw a little line there. So we want to start with our valence electrons. So sulfur is group 6. So is oxygen, and there's 2 of them. So that is 18 valence electrons that we should have here. Again, sulfur and oxygen, if you look on the periodic table, they are in the same group. And that means that oxygen should be more electronegative, which means definitely sulfur should be in the center. And that would mean we would have a sulfur, an oxygen, and an oxygen. We again would do 1 bond to the outside guys. That's going to be 2 4 electrons. That leaves us 14 more to go. They are going to go on the center guy, or not the center guy, the outside guys first, and in pairs. So that is 2 4 6 8 10 and 12. We have now put 16 electrons on the everybody here. We actually still have 2 more to go. And that's why this order of putting the electrons on properly is important, because that's how we get those 2 non-bonding electrons hanging out on the sulfur. Can't tell you how many people will draw this with no dots on that center atom. So again, you want to make sure that you follow the order there, outside first, and then work your way in. We then have now put 18 electrons, and by looking at it, hopefully you can see that oxygen is okay with 2 4 6 8 electrons, but sulfur is short there. It only has 6 electrons. In this particular case, both oxygens are identical to each other, which means, as we were just talking about, we can do a double bond on either one, remembering that we are bringing those electrons in to do so, and that would get us a Lewis structure that looks something like this. We also could have, if we wanted to, kind of double bond it on that side, so we actually can draw a resonance structure for this guy, where we actually double bonded the guy on the left, and it would look something like this. But the correct structure is this structure, and again, if you follow that order, you will get the right one and actually place those non-bonding electrons where they should go. Again, if you don't follow the order and just decide I'm going to double bond out of the chute, I can't tell you how many I've seen that look something like this, yes, and all that kind of stuff. So make sure that you do follow the order so that you end up with hopefully the right structure. Any questions on that particular one there? All right, then we'll go right in order there. So we'll shoot over to this guy, nitric acid. So we want to add up everybody that's there. So we got 1 valence electron for the hydrogen, 5 for the nitrogen, 3 oxygens, each at 6. That's a lot of math. That's 18, 19, 24 valence electrons. Again, this is slightly different than maybe you might anticipate how it's hooked together. But it is some type of arrangement like this. And we would follow the same sort of pattern. We would make 1 single bond. Here there's actually 2 center atoms, the nitrogen and the oxygen. The OH group here is actually what makes it an acid. That's actually the H that comes off this guy right here. So that's why we have this arrangement, and that's why the H is not attached to the nitrogen. Again, because this is essentially what makes it an acid pretty much right here. At this point, we have now used 2, 4, 6, 8 electrons. That leaves us something there, 16 to go. We're going to do our same approach. Obviously, hydrogen here is full. Cannot put any more electrons. Remember, no dots on the hydrogen. So we'll go over here then. This is the outside. So 2, 4, 6. That should fill that guy up. 8, 10, 12. That should fill that guy up. And at this point, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We still have 4 more electrons to go. That is going to then go to our next outside one, which is this oxygen. And it would get a couple of pairs of electrons. That has now placed pretty much all 24 electrons on this. Here, We want to make sure everybody's good, and hopefully you could recognize that everybody is good. Hydrogen is good. This oxygen here is good, 2, 4, 6, 8. Top oxygen, left oxygen is good, but our good friend nitrogen is not good. It has only 2, 4, and 6 electrons. So we then must make a double bond. In this case, we can make the double bond from this oxygen. We can make the double bond from this oxygen. You could double bond from this oxygen. Out of those three, probably this one is not your best choice, because this again is where that guy basically behaves like an acid. So we probably would want to double bond the other two. Again, we're going to bring a pair of electrons in to do that and make sure that we do erase it, and that will give us something that looks like this. We also could obviously draw a resin structure for that, where we double bond it to the left if you wanted to. That would be your other option here. Any questions on that particular one there? Okay. So I'm hoping you have some of these pictures here, just like we're drawing. We'll continue on then with Nh4 Plus, which is ammonium, and see what we got going. So let us go to Nh4 Plus. So again, there's 5 for our nitrogen. There is 4 hydrogens each at 1. And now we do have a +1 charge. So something with a positive charge means it lost an electron. We're going to get rid of that electron. And that is like 9 and 8 valence electrons in this particular case. Logical arrangement is obviously hydrogen can never be in the middle. So it's got to be nitrogen in the middle. We got to have hydrogens all about. We're going to do a single bond between the nitrogen and each of the outside guys. That actually is 2, 4, 6, 8. That's the total amount of electrons. Each hydrogen has 2. Nitrogen has 8. It is good to go. A little bracket around it to make it all nice and pretty. And then we would have our correct picture. Question on that one there. Okay. Continuing on, we'll come over here to H2S. So H2S here. Again, 2 hydrogens each at 1. Sulfur group 6, and that is 8 valence electrons. Same sort of reasoning as previous there. We cannot put the hydrogen in the middle, so obviously sulfur's got to find itself in the middle. We're going to put a hydrogen on each side. We're going to do 1 bond and 1 bond. That is 4 electrons from our 8. That means we have 4 more to go. Hydrogens on the outside is completely filled. So that means that the remaining 4 electrons should end up right there on the center atom in pairs. That gives the sulfur in the middle 8 electrons, which makes it perfectly good and happy. That gives each of the hydrogens 2 electrons, which also means it is happy. Any questions on that particular one there? Okay. And rolling through here, let's check our friend N2, which is nitrogen. So that is 2 times 5, which is 10 valence electrons. So you may be wondering, well, how do we go about this? There really is no center atom. It is just the 2 of them bound together. You could take the same approach, make 1 single bond between the 2. That's 2 electrons. The remaining 8 should go on the outside. So 2, 4, 6, and 8 at that point. That now has put on all 10 electrons. If we look at the nitrogen on the right, it's got 10. It's got 2, 4, 6, 8. Nitrogen on the left only has 4 electrons. So we do need to make a double bond here. Again, we can take any electrons we want. I'm going to take these two and erase them and bring them in to make that double bond. And when I make that double bond there by bringing those electrons in, nitrogen on the right has 2, 4, 6, 8, still good. Nitrogen on the left has 2, 4, 6, still not good. So this demonstrates here that we have used up all of our ability to make double bonds. So now we're going to try to fix it by making a triple bond. So again, I'm going to take these electrons here. I'm going to erase them basically and bring it in to make now my triple bond, since I've exhausted all of my double bond action there. And now if we look at nitrogen on the right has 2, 4, 6, 8 electrons. Nitrogen on the left has 2, 4, 6, 8 electrons. That is our correct structure. A little wobbly there, our triple bond, but there it is. That's how we get to a triple bond in something like nitrogen. Any questions on that there? So when you have at least 3 or more atoms, the element that ends up in the center, as to how you sort of choose which one should go in the center, it is typically the one that is the least electronegative. So the one that's sort of the least electronegative will basically find itself in the center. So if you look back at all the examples that we sort of did up to this point, for example, nitrogen is less electronegative than oxygen. Sulfur is less electronegative than oxygen. Nitrogen has to go there because hydrogen cannot go in the center. And I think that was everybody. Sulfur here, again, has to go in the center because hydrogen cannot. So typically it's the one that is the least electronegative. And like we've seen here in these examples, we never put hydrogen in the center, and we never typically find fluorine in the center because it's the most electronegative. Other questions? Okay. So we have one more to go here, which is our ClO3 minus. I won't quiz you on what that name is, but I'm going to go with chlorate on that name. I have a 1 out of 4 shot at that, I think it's being right. So ClO3, remember that this is actually Cl and not carbon. Sometimes people look at it quickly and go carbon because they see the C. But the Cl there is group 7. There's 3 oxygens at 6 each. Again, we do have a minus, so that means we want to add one more. A lot of them out there. That is 18, and 7 is 25, plus one more gives us 26 valence electrons. Now, in this particular case, chlorine and oxygen, chlorine is going to go in the center in this case. And again, in most cases, if you kind of look at something like this where you have one element and like 3 of some other element, usually that one element's going to be in the middle. So our Cl will be in the middle here. Oxygens will be around. We're going to do a single bond to everybody. That's going to use up 2, 4, 6 electrons. That leaves us 20 more to go. We're going to go with 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this particular point, we have now used up 24 electrons. We still got 2 more to go. Again, we go now to our center atom here, and we put a pair of electrons on there. That is now 26 electrons that have been placed on our picture. Every single oxygen is exactly the same, 2, 4, 6, 8. Chlorine, 2, 4, 6, 8. That is good to go, yes. And maybe a negative on the outside. If you follow these sort of steps that we've been talking about here in these examples and how to do these Lewis structures, you really should end up with I won't say always the perfect structure. And we're going to talk about when something may not be the best structure in just a second and how you determine that. But you will probably end up with a pretty good structure or the right structure by placing the electrons like this. So again, you don't want to do any type of piecework. You want to think about the total number of valence electrons as kind of like the total amount of electrons you're going to try to distribute to everybody within the molecule or ion, and not think about it as, well, nitrogen started with 5 valence electrons. I got to somehow get him like 3 more. Oxygen has 6, and how that all sort of comes together piece by piece. You want to think about the total number of valence electrons as what you needed to distribute across the molecule or ion. Any questions on how to draw Lewis structures clearly? You need to be able to draw Lewis structures correctly. Any questions on any of that there? Okay. All right, so then let's talk about sort of an aspect of Lewis structures that we look at. And this particular property, I guess, of Lewis structures, or a particular thing that we could calculate, can oftentimes help us decide, between maybe 2 different Lewis structures, which one might be a better structure than the other. And there definitely is Lewis structures that you could draw for the same ion or molecule that, you could maybe, depending on how you kind of hook everybody together or connect everybody, you may be able to come up with some different structures. So there actually is something that we could kind of use to help us decide, between different structures, which one might be better than another one. And one thing that does sort of help us with that is what is known as formal charge. So when we calculate the formal charge, we can basically calculate the formal charge of each element in a Lewis structure. So after you draw your Lewis structure, you basically go back through, and every single element that's basically in there, or atom that's in that Lewis structure, you could basically calculate the formal charge on it. And basically the formal charge is sort of, what the atom is sort of feeling in terms of, is it more positive or negative, how the electrons are being shared in that particular arrangement. To calculate the formal charge pretty much of a element within a Lewis structure, the formal charge as it is on the bottom there, you take the number of valence electrons in the free element. You then subtract the total number of non-bonding electrons, and those are the dots in your Lewis structure, minus 1/2 the number of bonding electrons, which are pretty much the lines in your Lewis structure. And when we talk about non-bonding electrons, we're not talking about non-bonding electron pairs. We're talking about individual electrons, basically. So if there's 3 electron pairs, that's 6 electrons, not 3. And again, this will sort of give us, what sort of the charge is of each of these guys in that particular arrangement in your Lewis structure. So let's take a look at ozone. Ozone looks something like this when you draw its Lewis structure. And we could actually calculate the formal charge on each of the oxygens that are present here. So let's take a look first off at, why not? Let's just go with the oxygen over here. So if we do that single bonded oxygen, the formal charge would be, oxygen normally has 6 valence electrons in it. In this arrangement, it has 2, 4, and 6 non-bonding electrons. So that would be -6. In this arrangement, it has 2 bonding electrons. So -1/2 of 2. That means that is 6 minus 6, which is 0, minus 1/2 of 2. That means in this arrangement, that single bonded oxygen is basically feeling a -1 charge in that arrangement. We then could do the same thing for the other oxygens that are present. So if we look at the oxygen over here, which is basically our double bonded oxygen. Our double bonded oxygen looks something like that. Also, because it is oxygen, going to normally have 6 valence electrons. It has in this configuration 4 non-bonding electrons, basically 4 dots, minus 1/2 of, it has a double bond. So each line represents 2 electrons. So that is 2 and 4 electrons there. And that is 6 minus 4, which is 2, minus 1/2 of 4, which is 2. That means that in this situation, the double bonded oxygen is feeling 0 in terms of its formal charge. Question on that calculation there. And we could also do it for the very last oxygen that I kind of scribbled all about. But if we look at that very last oxygen, we basically got a double bond coming in on one side. We got some dots up there on top and a single bond coming in on the other side. And if we did the formal charge for this guy, again, because it's oxygen, it would be 6. In this case, it has only 2 non-bonding electrons right there. Minus 1/2 of our 2, 4, 6 electrons. That is going to give us 6 minus 2, which is 4, minus 1/2 of 3, which gives us a +1 formal charge for this guy here. Overall, this thing is neutral because in this arrangement, the oxygen on the left has kind of a 0 charge. The oxygen in the middle is kind of carrying out a +1 charge in this arrangement, while the single bonded oxygen on the right is also carrying out a -1 charge, and that gives us 0 in this particular case. Any questions on that? How to calculate formal charge? All right, so why don't you try one here? So why don't we do our carbonate example there? For each of the elements, for the carbon, oxygen, oxygen, and oxygen, calculate the formal charge on each of them. So take a couple minutes and calculate the formal charge on all 3 of those, or actually all 4 of those atoms that are present in carbonate. So let us start with, doesn't really matter, I suppose. Let's start with this guy here. So that would be our single bonded oxygen. So just like we saw on the previous one, this is going to be 6 for the number of valence electrons in normal oxygen. In this particular case, it does have 2, 4, and 6 non-bonding electrons, minus 1/2 the number of bonding electrons, which is 2 because it has 1 line. And that is going to give us, in this particular case, 6 minus 6 minus 1/2 of 2. That is a -1. That means that the oxygen here is going to be -1. If we do the same thing for the oxygen on the right, it will come out exactly the same. So that's going to be -1. Let's look at the double bonded oxygen here. The double bonded oxygen would be, again, 6 because it's oxygen, minus 4 in this case because there are 4 non-bonding electrons, minus 1/2 of 4 as well, 2 there and 2 there. That gets us 6 minus 4, which is 2, minus 1/2 of 4, which is 2, and that's going to give us a formal charge of 0 on this particular case for that oxygen. And our good friend, the carbon there in the middle, looks something like that. Formal charge for this would be carbon, so that is group 4 in this case, minus 0 as there's no dots or non-bonded electrons present, minus 1/2 of our bonding, which in this case is 2, 4, 6, 8. And that would get us 0. That's basically 4 minus 4, which would be 0. So when we look at something like carbonate, which does have a -2 charge, we could see from the formal charge that essentially those -2 charge is coming from the 2 oxygens that are single bonded in this particular case. Any questions on that there? Questions on how to basically assign formal charges. So what is the benefit of sort of calculating the formal charges? Well, as I mentioned before, in addition to obviously you get a understanding of sort of what each of those atoms are feeling within sort of their bonding arrangement there in terms of their charge, we can actually use formal charge as a way to decide between multiple structures. So again, like I said before, it is possible you could draw, more than one Lewis structure for something. And you may think in your heart, well, I think this is a cool structure. It's probably right, or a good structure. And we can use formal charge to really sort of help us decide between sort of equivalent structures, Lewis structures, which one would be maybe the better structure or a better structure. So the general sort of guidelines for formal charge is this. When we do have neutral molecules, when we draw a Lewis structure where essentially we get like no formal charge, that is kind of the best situation. So if you could draw a Lewis structure where you really minimize the formal charge, that's usually going to lead to a fairly good Lewis structure. If we're able to minimize the sort of formal charge, either positive or negative guys, what we're essentially doing is, for in essence, making those electrons kind of being shared a little bit equally, and that's going to allow for a better sort of stronger structure in that sense. If you draw a Lewis structure and you end up with formal charges that are fairly large, like 2s and 3s, maybe 4s or something like that, it's probably not the best arrangement for that particular guy, how you put it together. When you're trying to decide between very similar distributions of formal charges in a Lewis structure, the one where we have the more negative formal charge on the more electronegative atom is probably the better structure. So when all else is sort of equal, if we have one where we have a positive formal charge on an electronegative atom versus one where the negative charge ends up on that more electronegative atom, the one with the negative charge is probably the better structure. So these are sort of general rules that will help you sort of decide between sort of arrangements of Lewis structures as to what might be the better arrangement. So let's take a look at sort of how we could kind of put this together here. Let's say we took something like formaldehyde, and maybe you decide, hey, I just want to kind of connect everybody in a row, like on the left, or maybe I want to have carbon as my central atom and everything connected to the carbon. And if you go through sort of the Lewis structure drawings for each of these, you will end up with perhaps these two drawings. So the goal here is to try to determine between these two, which one would be the better structure based on formal charge. So what I'll do is I'll give you a chance to decide that. So take a moment, calculate the formal charge on both of these structures, and you decide which one you think would be the better structure. And while you're at it, let's do another one. Let's do CO2. Let's say we double bonded CO2. Well, let's say we wanted to triple bond the CO2. So decide between these two structures, which one is better based on formal charge, and decide between these two structures, which one is better based on formal charge. So take a couple of minutes here, and then we will talk about which one would be better here. Finish out that structure for you. There you go. 1 minus 0, as there's no dots, minus 1/2 of 2, and that is going to give us a formal charge of 0. By the way, in case you haven't caught on, the formal charge will be the same for everybody that has that exact same arrangement, so we might as well just add it in over here as well. Now we'll look at the carbon that is there. Looks something like that. Formal charge on that carbon would be 4 for the carbon, minus 2 for the non-bonding electrons, minus 1/2 of 6 for the double bond and single bond on the other side. And that's going to be 4 minus 2, which is 2, minus 1/2 of 6, which is 3. That's going to give us a minus 1 in terms of the formal charge on that guy. Let's take a look at this oxygen, which is here. That oxygen's got a double bond, a couple electrons there and there. So the formal charge would be 6 minus 2, minus 1/2 of 6. That's going to be 6 minus 2, which is 4, minus 1/2 of 6, which is 3. That is going to give us a plus 1 on this guy. Finishing out our formal charges on the one on the right, we have a carbon that's got basically 2 bonds and a double bond. So that's going to be 4 minus 0 minus 1/2 of 8. And that is going to give us a 0 in terms of the formal charge. And our double bonded oxygen, like we saw previous, going to be 6 minus 4 for the non-bonding electrons or the dots. 1/2 of 4. That's going to be 6 minus 4, which is 2, minus 2 basically is 0. So now when we're comparing between these two sort of structures, we have 0 formal charges and minus 1 and plus 1, but our structure over here on the right pretty much has all zeros for the formal charge. And that's like the ideal situation. So based on formal charge, we would assume that the correct structure or the better structure should be the guy on the right because of that. In addition, the other thing that's not so great about the guy on the left is if we look at between oxygen and carbon, carbon is less electronegative, oxygen is more electronegative, but it is the oxygen that actually ends up with a more positive formal charge, which is not good either. We would have liked to see it with the more negative formal charge because of that. And that also means not such a great structure. Questions on that one on the left as to how we figure that out? Then let's take a look at the CO2 options. Again, like I said, you may draw on these things, go, I just feel like triple bonding can't be that bad, right? So let's see if it is bad or not so bad. We'll look at our singly bonded oxygen there, which is going to be 6 minus 6 minus 1/2 of 2. And that is going to give us a -1 for this guy. We have the carbon in the middle that has like a triple bond action going on there. That is going to be 4 minus 0 because there's no dots, minus 1/2 of 8. And that actually is going to get us 0 in this case for this guy. Then we got the triple bonded oxygen. So our triple bonded oxygen is 6 minus 2. Minus 1/2 of 6. And that is 6 minus 2, which is 4, minus 3, basically. And that's going to give us a +1 in this particular case. So with our triple bonded guy, we have a -1, a 0, and a +1. If we look at our CO2 double bonded, we have an oxygen on the left, which is this oxygen. And it has a formal charge of 0. So there's a guy on the other side. And we have basically a double bonded oxygen on each side. And that would be 4 minus 0 minus 1/2 of 8, which would be 0 as well. So again, in comparison to these two things, even though you go triple bond looks great, I like the way it looks. In comparison to these two things on formal charge, it actually is the better structure here, having the double bonded on both sides. Again, we really minimize the formal charge that we see. So this is a very good application of formal charge. you can use it to decide between different Lewis structures as to which one should be perhaps the better structure. Any questions on that or anything that we talked about here today? Okay, let's see a couple of things there. We are having lab today, which is Kool-Aid Lab, I think. So we'll talk a little bit about the lab. Then you could go off and do the lab. Also a reminder that this coming Tuesday is exam 1. Again, that's on chapter 1, 2, and again, the only thing from 3 that you need to worry about is the periodic trends for electronegativity and what electronegativity is, but no calculations like we did earlier in the week, but just in terms of the trends of what it is. We will take the exam during lecture time. We will do it kind of like we did our quiz. So again, you'll need to have that proper camera angle. And again, I'm thinking at this point, it's Tuesday's a long way away, so I haven't written it yet, but I'm thinking it'll be more like a written exam like we did the quiz, where again, you can print out the PDF and work on it, use paper if you don't have access to a printer and that type of thing. So a reminder that you will not be given any type of formulas, but you will be given a periodic table. You will be given any type of conversions or constants, and that type of stuff will be provided for you. It is a closed notes and closed book